Look at the space between your hand and the wall. Go ahead. Hold up your hand right now and look at the gap between your fingers and whatever surface is in front of you. What do you see? Nothing. Empty air. And if you pumped out all the air, what would be left? Nothing at all. A vacuum. The absence of everything. That's what you'd think anyway. That's what I thought for a long time. That's what everybody thinks because it seems so obviously true. Empty means empty. Nothing means nothing. What else could it possibly mean? Well, let me tell you something that took me years to fully appreciate, and I'm supposed to be good at this stuff. Empty space is not empty. Not even close. In fact, what we call empty space is one of the most complex, dynamic, furiously active things in the entire universe. It's seething with energy. It's bubbling with particles that pop into existence and vanish before you can catch them. It's humming with fields that never shut off. Not even for a moment. Not even at absolute zero. Not even if you removed every single atom and photon and speck of matter from a region of space. The nothing that remains is more interesting than almost anything we put into it. I know that sounds crazy. I know it sounds like I've finally lost my mind after all these years of staring at equations. But stick with me here, because this is one of the most beautiful and disturbing discoveries in all of physics. And once you understand it, you'll never look at empty space the same way again. You'll never look at anything the same way again. Let me start with a simple question. What is space? Not what's in space, but space itself. The empty container that holds everything. We grow up thinking of space as a kind of stage, a big three-dimensional grid where things happen. Objects move through space. Light travels through space. But space itself is just there, doing nothing, being nothing. It's the backdrop, the empty theater before the actors arrive. This picture comes from Newton. Good old Isaac Newton, who figured out gravity and motion and gave us a framework that worked brilliantly for 200 years. In Newton's universe, space is absolute. It's fixed. It's the same everywhere and everyone. It's like a giant invisible box that contains everything but is itself featureless and inert. Empty space, in this view, is truly empty. It has no properties. It does nothing. It just is. But then along came Einstein. And Einstein showed us that space is not what Newton thought. Space is not a fixed stage. It's more like a fabric. It bends and curves and stretches in response to matter and energy. Massive objects warp the space around them, and that warping is what we experience as gravity. The Earth doesn't pull you down through some mysterious force acting at a distance. The Earth bends the space around it, and you follow the curves. Space is not passive. Space is dynamic. Space does things. Now, that's already a big change from the Newtonian picture. But Einstein was still working with what we call classical physics. Space might be dynamic, but it's still smooth. It's still continuous. It's still, in some sense, empty when you take away all the matter and radiation. Einstein's space can curve, but it doesn't have stuff in it unless you put stuff in it. And then came quantum mechanics. And quantum mechanics changes everything. Again, here's what you need to understand about quantum mechanics. In the quantum world, nothing is ever perfectly still. Nothing is ever completely at rest. There's always a minimum amount of jiggling, a minimum amount of uncertainty, a minimum amount of activity that can never be eliminated no matter what you do. This is not a limitation of our instruments. It's not that we can't measure things precisely enough. It's built into the fabric of reality itself. The universe has a kind of restlessness that cannot be removed. You see this most clearly in what we call the Heisenberg uncertainty principle. Werner Heisenberg figured out that you cannot simultaneously know both the position and the momentum of a particle with perfect precision. The more precisely you know one, the less precisely you can know the other. This isn't about measurement errors. This is about the nature of reality. A particle does not have a definite position and a definite momentum at the same time. It's fundamentally uncertain. It's fuzzy. It's spread out across possibilities. Now, what does this have to do with empty space? Everything. Because the uncertainty principle doesn't just apply to particles. It applies to fields. And in modern physics, fields are fundamental. Let me explain what I mean by that. When I was working on quantum electrodynamics back in the 1940s, along with Julian Schwinger and Shinichiro Tominaga, we developed a picture of reality that's quite different from what most people imagine. In this picture, the fundamental things are not particles. The fundamental things are fields. There's an electron field that fills all of space. There's an electromagnetic field that fills all of space. There are fields for quarks and neutrinos, and all the other particles we've discovered. These fields are everywhere, all the time, extending throughout the entire universe. What we call particles are actually excitations of these fields. Ripples, vibrations. When the electron field vibrates in a certain way, we see an electron. When the electromagnetic field vibrates, we see a photon. The particle is not a little ball sitting in empty space. The particle is a pattern in the field, a localized disturbance, a concentrated bit of field energy that behaves like a thing. Now, here's where it gets interesting. The uncertainty principle tells us that these fields cannot be perfectly still. Even in their lowest energy state, even when there are no particles around, the fields are fluctuating. They're jiggling. They're oscillating randomly and unpredictably at every point in space. This is not optional. This is required by the mathematics. This is required by the fundamental structure of quantum mechanics. Think about what this means. Take a region of space and remove everything from it. Every atom, every photon, every particle of any kind. Cool it down to absolute zero, so there's no thermal energy. Isolate it completely from the rest of the universe. What you have left is what physicists call the vacuum, the quantum vacuum, and that vacuum is not empty. It's filled with fluctuating fields. It's seething with what we call zero-point energy, the lowest possible energy, but not zero energy. There's always something there. Always. These fluctuations are not just mathematical abstractions. They have physical consequences. Real, measurable consequences that we can detect in the laboratory. Let me tell you about one of the most beautiful experiments in physics. It's called the Casimir effect, named after Hendrik Casimir, who predicted it in 1948. Here's the setup. Take two metal plates and put them very close together. I'm talking about separations of less than a micrometer. Now, in classical physics, if you remove all the matter and radiation from between the plates, there's nothing there. No force should act between them except maybe some residual electrical attraction. But in quantum physics, something strange happens. The plates are pushed together by an invisible force. They attract each other for no apparent reason. Why does this happen? Because of the vacuum fluctuations. You see, the quantum fields are fluctuating everywhere, both inside and outside the plates. But the plates impose boundary conditions. Only certain wavelengths of fluctuation can fit between the plates, while outside, all wavelengths are allowed. This means there are more fluctuations outside than inside, more fluctuations pushing in than pushing out. And so the plates get pushed together by the pressure of empty space itself. I want you to appreciate how remarkable this is. The plates are being pushed together by nothing, by the void, by empty space. Except empty space isn't empty. It's full of energy, full of fluctuations, full of something that can exert a physical force on matter. The Casimir effect has been measured with extraordinary precision. It matches the theoretical predictions beautifully. This is not speculation. This is confirmed physics. But let me tell you about something even stranger. The vacuum fluctuations don't just push plates together. They create particles, real particles, popping into existence out of nothing and then vanishing again almost immediately. We call these virtual particles, but don't let the name fool you. The word virtual makes them sound less real than ordinary particles. But they're not less real. They're just short-lived. They borrow energy from the vacuum for a brief moment, do their thing, and then pay it back. The uncertainty principle allows this. If the time is short enough, the energy can be uncertain enough for particles to appear and disappear without violating any conservation laws. Picture what this means for empty space. It's not a static void. It's more like a roiling sea. Particles and antiparticles are constantly appearing in pairs, existing for an unimaginably brief instant, and then annihilating each other and vanishing. Electrons and positrons, quarks and antiquarks, even pairs of heavier particles, though more rarely. The vacuum is fizzing with these virtual pairs all the time, everywhere. It's like space is boiling at the quantum level, perpetually bubbling with the ghosts of particles that almost exist. Now you might ask, if all this is happening, why don't we notice it in everyday life? Why does empty space look empty to us? The answer is that these fluctuations happen on incredibly small scales and incredibly short times. We're talking about distances smaller than atoms. We're talking about times shorter than a billionth of a second. Our eyes, our instruments, our everyday experience, all of it operates at scales vastly larger than these quantum fluctuations. We average over them. We smooth them out. The foam and fizz of the quantum vacuum gets blurred into what looks like perfect smoothness. It's like looking at the ocean from an airplane. From up high, the ocean looks flat and calm. Maybe you see some gentle swells, but the surface appears smooth. Now get in a rowboat and you'll see waves. Get closer and you'll see smaller ripples. Stick your finger in the water and you'll feel individual molecules bouncing around chaotically. The smoothness was an illusion of scale. The closer you look, the more turbulent it gets. Space is the same way. The closer you look, the more you see the quantum bubbling that underlies everything. But here's what really gets me. Here's what keeps me up at night when I think about these things. The energy in those vacuum fluctuations is enormous. I don't mean a little bit of energy. I mean a staggering, incomprehensible amount of energy. If you tried to add up all the zero-point energy in even a small region of space, you'd get numbers that don't make sense. Numbers that are larger than anything we know how to deal with. Let me be more precise. When we calculate the energy density of the quantum vacuum using our best theories, we get a number that's about 120 orders of magnitude larger than what we observe. That's not 120 times larger. That's 10 to the 120th power times larger. A 1 followed by 120 zeros. This is, without exaggeration, the worst prediction in the history of physics. We call it the cosmological constant problem, and nobody knows how to solve it. What does this mean? It means one of two things. Either our theory is wrong in some fundamental way that we don't understand, or there's some cancellation happening. Some mechanism that reduces this enormous energy to almost but not quite zero. Neither option is comforting. Either we're missing something huge about the nature of reality, or there's a fine-tuning so precise that it defies comprehension. This is one of the great unsolved problems in physics. The vacuum, which we thought was nothing, has become one of the deepest mysteries in all of science. And it gets even more interesting when you bring gravity into the picture. You see, in Einstein's theory, energy gravitates. It bends space. It has weight. So if the vacuum has energy, and we know it does because of the Casimir effect and other phenomena, then the vacuum should gravitate. Empty space should have a gravitational effect. And here's the thing, it does. In 1998, astronomers made a shocking discovery. The expansion of the universe is not slowing down, as everyone expected. It's speeding up. Galaxies are flying apart from each other faster and faster as time goes on. Something is pushing the universe apart, some kind of anti-gravity effect that's built into space itself. We call this dark energy. And the best explanation we have is that it's the energy of the vacuum, the energy of empty space. The nothing that turns out to be something is actually driving the evolution of the entire cosmos. Think about that for a moment. The vacuum fluctuations we detected between tiny metal plates in a laboratory are the same phenomenon that's determining the ultimate fate of the universe. The fizzing of empty space at the quantum level is connected to the accelerating expansion of everything, everywhere, on the largest scales imaginable. The very small and the very large are linked through the nature of the vacuum, through the nature of nothing. Now, I've been talking a lot about what we know, but let me be honest with you about what we don't know. Because in science, it's just as important to understand the limits of our knowledge as it is to understand the knowledge itself. Maybe more important. We don't understand why the vacuum energy is so small compared to our calculations. We don't understand the exact nature of dark energy, whether it really is vacuum energy or something else entirely. We don't have a complete theory that combines quantum mechanics with gravity, and until we do, our picture of the vacuum is necessarily incomplete. We're working with approximations, good approximations in most cases, but approximations nonetheless. And there's something else, something deeper that I've thought about a lot over the years. Even if we had a complete theory, even if we could calculate everything perfectly, would we really understand what the vacuum is? Would we understand why there's something rather than nothing? Would we understand why the laws of physics are the way they are, why the fields exist, why anything exists at all? These questions take us to the edge of physics, to the boundary where science meets philosophy. I don't have answers to them. Nobody does. But I think they're worth asking. I think they're worth sitting with. Because when you stare into what you thought was empty space and realize it's anything but empty, you're confronted with the fundamental strangeness of existence itself. Let me try to paint a picture for you of what empty space really is, based on everything we've learned. Imagine you're shrinking down, smaller and smaller, past atoms, past nuclei, past quarks, down to the smallest scales we can describe with our theories. What do you see? You see space-time itself becoming uncertain, fuzzy. The smooth fabric that Einstein described starts to look like foam. Tiny wormholes and black holes and loops of space popping in and out of existence. The geometry of space fluctuates wildly. This is what we call quantum foam, and it's the deepest level of reality we can currently conceive of. And pervading all of this, you see the fields. The electron field fluctuating, the quark fields fluctuating, the electromagnetic field fluctuating, all of them doing their quantum jiggle, creating and destroying virtual particles, exchanging energy in ways that never stop and can never be turned off. This is what fills what we call empty space. Not nothing, but everything. A seething, bubbling, infinitely complex dynamical system that underlies all of matter and energy, and even space-time itself. The void is full. The nothing is something. The emptiness is pregnant with possibility. And here's what I find most beautiful about all this. Every particle you see, every atom in your body, every photon of light that hits your eyes emerges from this vacuum. The vacuum is not just the absence of particles. It's the source of particles. It's where they come from and where they return to. When an electron and a positron annihilate, they don't disappear into nothing. They return to the field, their energy redistributed into the fluctuations of the vacuum. When a photon is emitted from an atom, it doesn't come from nothing. It's an excitation of the electromagnetic field, which was already there, already fluctuating, already waiting to be disturbed. You are made of the vacuum. Everything you see around you is made of the vacuum. The entire visible universe is just the vacuum in an excited state. Ripples on the surface of an infinite sea. Patterns in a field that extends everywhere and never stops moving. You are not in space. You are of space. You are a configuration of the fields that fill space. A particular arrangement of excitations. a temporary pattern in the eternal dance of the quantum vacuum. I remember when I first really understood this, really felt it, rather than just calculating it. It changed how I saw everything. That table over there is not a solid object sitting in empty space. It's a collection of field excitations, patterns of energy, stable configurations of the same underlying fields that fill what we call emptiness. The boundary between the table and the space around it is not as sharp as it looks. They're made of the same stuff, different modes of the same fields. The table is condensed vacuum, if you want to think of it that way. And the vacuum is potential tables, potential stars, potential everything. This connects to something I've always felt about physics, something that keeps me going through the hard calculations and the frustrating dead ends. The universe is fundamentally unified. It's not made of separate pieces cobbled together. It's one thing, expressing itself in different ways. The fields are everywhere. The vacuum is everywhere. And everything we see is just the vacuum talking to itself, finding patterns, exploring possibilities. Some people find this reductionist view cold or alienating. They think that explaining things in terms of fields and quantum fluctuations somehow diminishes them. I've never understood that. To me, it makes everything more wonderful, more magical, if I can use that word without being misunderstood. Here's this incredibly simple thing, this set of fields obeying mathematical laws, and out of it emerges galaxies and stars and planets, and oceans and trees and human beings having conversations about the nature of reality. The simplicity at the bottom gives rise to all this complexity at the top. How could that not be beautiful? How could that not fill you with awe? And we're still discovering. That's what I want you to take away from all of this. We're still learning what empty space really is. The cosmological constant problem remains unsolved. The unification of quantum mechanics and gravity remains incomplete. There are mysteries in that fizzing nothingness that we haven't even learned how to formulate properly yet. Some physicists think the vacuum holds the key to everything. That once we truly understand what empty space is, we'll understand where the universe came from and why it has the properties it does. Maybe the Big Bang itself was a kind of vacuum fluctuation, a quantum bubble that expanded and became everything we see. Maybe there are other bubbles out there, other universes with different properties, a vast multiverse of possibilities, all emerging from the fundamental uncertainty of the quantum vacuum. These ideas are speculative, but they're not crazy. They follow naturally from what we know about the nature of emptiness. Other physicists think we need an entirely new framework, something beyond quantum field theory, to really understand the vacuum. String theory suggests that the fields we see are actually made of tiny vibrating strings, and the vacuum is the state where all those strings are in their lowest energy configuration. Loop quantum gravity suggests that space itself is quantized, made of discrete chunks, and what we call the vacuum is a particular arrangement of those chunks. Nobody knows which approach, if any, is correct, but everybody agrees that understanding the vacuum is crucial. Let me bring this back to something personal, something you can carry with you when you leave this lecture and go about your life. You're never alone. Even in the deepest isolation, even in the emptiest void you can imagine, you're surrounded by the quantum fluctuations of the fields. A vacuum is there. The potential for everything is there. You exist because the vacuum can be excited, can be shaped into patterns, can form stable structures that we call matter. You are the vacuum's way of knowing itself. And when you look at empty space, when you look at that gap between your hand and the wall where you see nothing at all, I want you to remember what's really there. The fields are there, fluctuating. The virtual particles are there, appearing and vanishing. The zero-point energy is there, an irreducible quantum of activity that never stops. Dark energy is there, pushing the universe apart. The potential for anything that could ever exist is there, latent in the fluctuations, waiting to be actualized. Empty space is the fullest thing there is. That's the paradox. That's the truth that physics has revealed. The nothing that we see is actually everything that could be. The void is infinite possibility. The absence is pure presence, doing its quantum dance at every point, in every moment, forever. I've spent my life trying to understand nature, trying to figure out the rules, the laws, the deep patterns that underlie everything. And one of the most profound things I've learned is that what we call nothing is anything but. The vacuum is not empty. Space is not passive. The stage is part of the performance. And when you really understand that, when you really feel it in your bones, you see the world differently. You see yourself differently. You see everything as part of one vast, unified, endlessly creative process. The quantum fields doing their eternal dance, and you're part of that dance. You're made of that dance, and the dance never ends. That's what empty space is. That's what nothing is. It's everything waiting to happen. And that, to me, is more wonderful than any mystery I could have imagined.